Hello friends, I am back with the part 5 lecture of atomic structure series, and today it will be the concluding lecture of the subject atomic structure, which is the basic for students of physics and chemistry. So till now we have seen how the subatomic particles were discovered and how Rutherford discovered nucleus. Then came the important Planck quantum theory, which revolutionized physics. Then those theories was incorporated in photoelectric effect by Albert Einstein, then by Bohr, and so the story continued. So in this part 5 lecture, today I'll be basically discussing the wave mechanical model of atom, which is another revolutionary concept of physics. So friends, let's start with my PowerPoint. So here we come, atomic structure, part 5. Myself, Vedanta Kumar Bora, Associate Professor, Department of Chemistry, DR College, Assam, India. You can mail me at vedanta69@gmail.com. So after going through this presentation or after watching this video, you feel that you have some queries, you have some doubt, then you are most welcome to mail me in my ID as given below. And I promise that I will try to clear your doubt. So as I told you, today my topic will be the wave mechanics, that is the quantum mechanics. So I will discuss the quantum mechanical model of atom, and I will discuss how this model was developed. So now first of all, I would like to answer what is quantum mechanics. Quantum mechanics holds the view that like light, all material particles have dual nature. That is, they have both wave nature and particle nature. And quantum mechanics is a science dealing with the behavior of matter and light on the atomic and subatomic particle. So here is some restriction regarding quantum mechanics, that quantum mechanics holds good only for microscopic particle, not for macroscopic particle. So quantum mechanics can explain the properties of subatomic particles. It can explain the properties of atom, it can explain the properties of proton, it can explain the properties of neutron, it can explain the other subatomic particles like quarks and gluon. Because in the proceeding slide we will see that all microscopic particles, they have both wave character and the particle nature. In fact, wave nature is associated with all particles, but as the size of the particle decreases, as the mass of the particle decreases, the wave particle become more prominent, and that is what quantum mechanics deals. So now I will tell you what is a matter wave. So this gentleman, Louis de Broglie, so he won the Nobel Prize, and you will be astonished to hear that Louis de Broglie, he won the Nobel Prize for physics, and his basic education was history. He had a master's degree in history, and during the First World War he joined voluntary army for France, and there he was given the duty in the army signal corps, and there he was using instruments like radio, telegram, etc., and where he got attracted to physics. So once the World War was over, he came back home and he started reading books of physics and mathematics of his elder brother, who happened to be a school teacher. And the story continued, and any doubt he had, and he used to clear it from his elder brother. And then he again brought a revolutionary idea to the mind of the physics, and he proposed what we know as de Broglie hypothesis. And what did de Broglie spoke in his hypothesis? Then according to de Broglie, all moving particle is also associated with wave. Because that time it was established that light, it has both wave nature as well as particle nature. And Einstein proposed that light has got dual character. That means it can manifest as wave as well as it can manifest as particle. So some properties of light can be explained by assuming light is wave. For example, you can explain interference. You can explain diffraction by considering light as a wave. On the other hand, like other phenomena of light, like reflection, refraction, photoelectric effect, they can be explained by assuming light as a particle. So Einstein forwarded that light has got dual character. That means it can manifest as wave as well as particle. So this idea was extended by Louis de Broglie to all moving material particle, that light moving particle is also associated with a wave, but this wave is known as matter wave, and they differ from electromagnetic wave. How does matter wave differ from electromagnetic wave? Electromagnetic wave travel with a velocity equal that of light, but matter wave, they move with different kind of velocity. Then electromagnetic wave, they is associated with electric field and magnetic field, but matter wave is not associated with electric field and magnetic field. So any moving particle, whether it is a moving cricket ball or whether it is a moving bird or whether it is a moving electron or whether it is a moving proton, they too has got wave nature, and the wave that is associated with a matter wave is called wave associated with a moving particle is called matter wave. And then de Broglie proposed a relationship between the wavelength of matter wave and the momentum, and this is the relationship lambda, that is the wavelength of the matter wave, is equal to h by mv. H is the Planck's constant, m is the mass of the moving particle, v is the velocity of the moving particle. So that means the wave, since h, that is the Planck's constant, it is a constant, so the wavelength of matter wave will be inversely proportional to its momentum. M stands for mass, v stands for velocity, so mv is momentum. Okay, am I right? So from this equation you can see, as the momentum of the particle increases, the wavelength will decrease. Now what is the mass of an electron? The mass of an electron is 9.11 into 10 to the power of minus 28 gram. Then what is the momentum mass of a cricket ball? It is around 400 gram, it is around 300 gram. So a cricket ball is having much higher mass than a moving electron. So as the mass increases, momentum will increase, and when momentum increases, wavelength will decrease. And that is the reason that when a fielder throws a cricket ball, then we do not see the wave character, we do not see the vibrational motion of the cricket ball. It is because the momentum of a moving cricket ball is much higher compared to the momentum of a moving electron, because the mass of a cricket ball is much higher than the mass of an electron, and as a result the wavelength of a moving cricket ball is very short, and that is why we do not observe its wave character. So here what you see, that as the momentum of the particle decreases, that means as we go for microscopic particle, wavelength will increase, and for macroscopic particle, wavelength will decrease. That means for microscopic particle, the wave will be more distinct than macroscopic particle. So at the beginning of the lecture, I told you that wave mechanics is applicable to microscopic particle, not to macroscopic particle, because wave mechanics or quantum mechanics, it takes in consideration of the wave nature of the particle. So as the mass of the particle decreases, the wavelength increases and the wave character becomes more distinct. I hope my students are clear with de Broglie hypothesis. So again, just a recap. So de Broglie hypothesis states that wave is associated with all moving particle, and the wave associated with a moving particle is called material wave. Okay, now let's go to my next slide. So here, this is the orbit as proposed by Bohr. This is a circular orbit, and if we go by de Broglie hypothesis, then the particle will not move in the circular path, which is called orbit. In fact, it will have a wave motion. And here, what you say that de Broglie hypothesis is bringing some defect to Bohr's model, because in Bohr's model, what you observed that the electron is treated as a particle and it moved in a fixed orbit, and that fixed orbit is at a fixed distance from the nucleus. But if we go for the wave model of the electron, that means the electron is moving in wave. So the electron is not spending its all time in the orbit. Sometimes it is going away from the orbit, and sometimes it is coming closer to the nucleus. Okay, so this is an orbit which we call in phase, because the wavelength is a simple whole number of the orbit, and here this wave, it is called the out of phase. Then what happened? So here what you see, that if you consider electron to be a particle, then the electron will spend all its time moving around this orbit, and the orbit is at a fixed distance from the nucleus. So we can determine exactly the position of the electron, because it is at a fixed distance from the nucleus. But once if you consider the wave motion of the electron, it is moving in wave. Here you can see that the electron is not at a fixed position from the nucleus. That means it is not possible to exactly determine the position of the electron due to its wave motion around the nucleus. And this was extended by Heisenberg, and he proposed the Heisenberg Uncertainty Principle. And what does Heisenberg Uncertainty Principle states? So wave mechanics, electron do emit light in certain wavelength based on their energy levels, And since waves spread out from the electron, the wave mechanical model predicts an area where an electron would be found and not a specific place where it will be found. So Bohr proposed that electron will be present in a specific place because the electron will be revolving around the nucleus in the circular particle orbit, and the orbit is at a fixed distance from the nucleus. But the wave mechanical model, if you go for the electron wave, you have clearly seen here that the electron is not spending all the time in the fixed path, so its specific position is not certain. You cannot exactly determine the position of the electron around the nucleus because of its wave motion. So then comes the Heisenberg Uncertainty Principle. So Heisenberg Uncertainty Principle states that you cannot measure simultaneously both the momentum and exact position of an electron at the same time. So what I was talking about, that since the electron is having wave, it is also showing wave motion. So when it revolves around the nucleus, it is moving in a wave, and due to the wave motion, it is not having the same specific path. It is not exactly located at the same distance from the nucleus. That means it is not possible to measure simultaneously both position and momentum of a moving subatomic particle like electron. But what else? What you can tell now with the Heisenberg Uncertainty Principle, the Bohr's concept of orbit is now meaningless. Because in Bohr's orbit, you can exactly determine the position of the electron. That means the electron is at a fixed distance from the nucleus. But by Heisenberg Uncertainty Principle, it is not possible to determine exactly simultaneously both position and momentum of a moving electron. That means the exact position of electron cannot be determined. So the Bohr concept of orbit is now meaningless. So what we can tell regarding the position of electron is certain region where there is a probability of finding the electron, and this region around the nucleus, the three-dimensional region around the nucleus where there is a probability of finding electron, is called atomic orbital. So here in this slide I can show, so this was orbit, Bohr orbit, and if the electron is present in the orbit, it will always move at a fixed distance from the nucleus. So the probability, so it is exactly possible to determine the position of the electron. But if we go for the wave motion, the electron may be here, the electron may be here, the electron may be here, the electron may be here. That means the position of the electron from the nucleus is not fixed. Sometimes it increases, sometimes it decreases. But overall, the electron may be found within this region, from this region to this region, from this region to this region, and this region has the probability of finding the electron, and this region is called atomic orbital. So again, Heisenberg Uncertainty Principle pointed finger toward Bohr's atomic theory, and with the advent of de Broglie hypothesis and Heisenberg Uncertainty Principle, the Bohr's concept of orbit was discarded, and the orbit is replaced by a new word called atomic orbital. And what is atomic orbital? It is a three-dimensional region around the nucleus where there is a maximum probability of finding electron. And moreover, Heisenberg gave an uncertainty relationship. This is called the uncertainty relationship. Delta X, it is the uncertainty in position, because you cannot determine the exact position of an electron. And when you determine the position of an electron, there will be some error, and that error is called uncertainty. And similarly, you cannot determine the exact momentum of the electron. And when you measure the momentum of an electron, there will be some error, and that error is called uncertainty. And Heisenberg uncertainty relationship states delta X, delta B is greater than or equal to h by 4 pi, where h is called the Planck's constant. So here what I am trying to show, this is the nucleus, and these are the region where there is a probability of finding electron. The dot may represent the position of electron. So in this specified region around the nucleus where you can find the probability of electron is called orbital. Then what happens that when Bohr proposes atomic theory, he considered electron to be a particle. And assuming electron to be a particle, he could calculate the energy of electron, he could calculate the radius of the orbit, and so and so. But de Broglie hypothesis made people believe, made physicists believe that electron also has wave motion. So now you need a motion to explain the wave nature of electron. And it was Schrodinger who proposed a wave equation, and that wave equation is called Schrodinger wave equation. The Schrodinger equation, sometimes called the Schrodinger wave equation, is a partial differential equation. It uses the concept of energy conservation, that is kinetic energy plus potential energy is total energy, to obtain information about the behavior of an electron bound to the nucleus. It does this by allowing an electron wave function psi to be calculated. So this is what it looks. This is the Schrodinger wave equation. So the name itself speaks Schrodinger wave equation. That means he considered the wave motion of the electron and he deduced an equation, and that equation is helped to calculate the value of psi, and this is psi is called the wave function. And here is called the total energy of the system, and total energy E, it is equal to the kinetic energy plus potential energy. So this is a time independent equation of Schrodinger, and this Schrodinger wave equation can also be written in some other form. These are the other form. This is a del square psi by del x square plus del square psi by del y square plus del square psi by del z square. So this is the Schrodinger wave equation in 3 dimension, because we are considering the 3 axes. We are considering the x-axis, we are considering the y-axis, we are considering the z-axis. And here m, it represents the mass of the electron, h is the Planck's constant, and E, it is the total energy of the electron, and V is the potential energy. And this psi, it is called the wave function. So we can write like this also. This is the Schrodinger wave equation, and this is delta square, and it is also called the Laplacian operator. So we can write Schrodinger wave equation in different form. We can write it like this. So here this delta square, it is called the Laplacian operator. You can write, this is the simplest form of Schrodinger wave equation in 3 dimension. And if somebody tells you to write Schrodinger wave equation in 1 dimension, then you have to omit these 2 terms, because this is y-axis and z-axis. These are the 2 terms. You have to omit it. Then your Schrodinger wave equation will become del square psi by del x square. Because it is in 1 dimension, we will consider the movement of electron in only 1 axis, that is x-axis. And if you consider the 3 dimension, then you will consider the 3 axis, x, y, and z-axis. So when you write the Schrodinger wave equation in 1 axis, you simply omit these 2 terms. You omit these 2 terms, and your equation will be del square psi by del x square plus 8 pi square m by a square e minus v psi is equal to 0. So this is how we write Schrodinger wave equation, and this is also how we write Schrodinger wave equation. Here it is delta square. It is called the Laplacian operator. So solving the Schrodinger wave equation gives us psi and psi square. So by solving Schrodinger wave equation, we can find out the value of psi, that is the wave function, and psi square, that is square of the wave function. And from this wave function, we get quantum numbers. And these quantum numbers will determine the energy, the shape, the orientation of the orbitals. So which I will be discussing after 1 or 2 more slides. Then the question comes, what is the physical significance of this wave function psi? So we have written the Schrodinger wave equation, and why we need Schrodinger wave equation? To describe the motion of electron by considering its wave property. And by solving Schrodinger wave equation, we can find out the value of the wave function psi or psi square. Now the question was, what is the physical significance of the wave function? And the physical significance of wave function was given by Born. And according to Born, the wave function psi itself have no physical significance. So simply psi, the wave function, has got no simple physical significance, but its square, that is psi square or modular psi square, if psi is imaginary, it has the physical significance, and it will give you the probability of finding an electron at a particular time at a particular point. So this is very important. So what is the physical significance of the wave function? The wave function psi itself has got no physical significance. It has got no meaning. But the square of the wave function has got physical significance. And the square of the wave function will give you the probability of finding the electron in a given region around the nucleus in a given time. So the quantum mechanical model of atom, already I told you that the quantum mechanical model of atom, by solving Schrodinger wave equation, you get different values of the wave function psi. And from psi, you get 4 different types of quantum number. Now, first of all, I will just want to tell you what are quantum number. Quantum numbers are set of numbers which identify electrons in an atom. So quantum numbers represent identity number of electrons. Now, what are your identity? So suppose you and your friend, they're in the same school. So if I ask you to write your complete address, first of all, you will write your name, then you will write the name of your school name, then you will write down the name of your class, then you will write down the name of your section, whether it is section A or section B, then you will write down your roll number. So if these informations are present, your name, the name of your school, the name, your class, then the section to which you belong, and the roll number, then anybody can identify you. So similarly, if you consider an atom to be a school and the electrons has students, so there are many students in the school and each student will be represented by some number, and these numbers are quantum numbers, and these numbers will help you to identify the electrons present in the atom. Now, what are these quantum number? So there are 4 quantum numbers. One quantum number, it will tell you about the distance of the electron from the nucleus. It is called the principal quantum number. Then there is another quantum number. It will represent the energy sublevel, which is called the azimuthal quantum number. Then there will be another quantum number which will represent the orientation of the sublevels in electric field in space. It is called the magnetic quantum number. And the last one, the quantum number, which will tell you the direction of electron spin, because the electron, when it moves around the nucleus, also have a spinning motion like the planet spins in its orbit. So these are the 4 different types of quantum number. This one will be called the principal quantum number. This one will be called the azimuthal quantum number. This one will be called the magnetic quantum number. And this one will be called the spin quantum number. So principal quantum number, it is represented by small n, and it describes the mean energy level of the electron in terms of its distance from the nucleus. So already told you that in Bohr's model, the orbits, now we do not call it as orbits, and the orbits were also called energy levels, and these energy levels are represented by the principal quantum number. So the first energy level, it is n is equal to 1. Second energy level, n is equal to 2. Third energy level, n is equal to 3. So as the number increases, as the value of principal quantum number increases, which means the electron is away from the nucleus and the energy of the electron will increase as the value of principal quantum number will increase. So the principal quantum number n, it may have value 1, 2, 3, 4, 5, etc. So when n is equal to 1, it means the electron belongs to the first energy level, and the first energy level is also called the K cell. So this alphabets K, L, M, N is used to designate the values of principal quantum number. So n is equal to 1 means first energy level closest to the nucleus, it is called the K shell. N is equal to 2, it is called the second energy level, and the second energy level will be represented by the alphabet L. So L cell means second energy level, M cell means third energy level, so and so. Then the next quantum number, it is called the angular momentum quantum number or the azimuthal quantum number. It is also called the azimuthal quantum number. It is also sometimes called the angular momentum quantum number, and sometimes it is also called the subsidiary quantum number. So it will represent the energy level within the main energy level. For example, in your school, suppose class 10 is the mean energy level, and the class 10 may have 2 sections, section A and section B, which can be considered to be the subcells. So each cell is further divided into subcells. Each energy level is further divided into sub-energy levels, and these sub-energy levels are represented by the angular momentum quantum number or azimuthal quantum number. Now the values of L will depend upon the value of N. For each value of N, L may have value 0, 1, 2, 3, 4, etc. And the azimuthal quantum number are represented by the alphabets S, P, D, F. So here you should note down that these alphabets are small case, whereas the principal quantum number, the quantum numbers are also represented by alphabets K, L, M, N, and they were in the uppercase. So the angular momentum quantum number or the azimuthal quantum number is represented by L, and the value of N will depend upon value of L will depend upon the value of N, and for each value of N, L may have value from 0 to N minus 1, and the alphabets S, P, D, F is used to designate the values of N. And the physical significance of the azimuthal quantum number is that they determine the shape of atomic orbital. So the physical significance is important. The main physical significance of the azimuthal quantum number is that the shape of atomic orbital is determined by the azimuthal quantum number. So here I can show you if the principal quantum number N is equal to 1, that means K shell. So when N is equal to 1, L will be 0 because N value will be from 0 to N minus 1, 1 minus 1, 0. N is equal to 2. N is equal to 2 means L shell. And so when N is equal to 2, L may have value 0 and 1. So L may have value 0, L is equal may have value 1. 0 means S subcell, L 1 means P subcell. So that means L shell has got two subcell, that is S and P subcell, which are represented as 2S and 2P subcell. There will be no 2D subcell, because for 2D subcell D will be equal to 2, and for N is equal to 2, L may have value only 0 and 1. L cannot have value 2, and since L cannot have value 2, and when L is equal to 2, it means D subcell. That means 2D subcell does not exist. So students, I think it is clear. Then when N is equal to 3, it is the M cell, and for N is equal to 3, L will have value 0, 1 and 2. Maximum value of L is N minus 1. So when N is equal to 3, L may have value, maximum value is 3 minus 1, that is 2. L is equal to 0, S subcell, L is equal to 1, P subcell, L is equal to 2, D subcell. So M cell has only S, P and D subcell, which are represented as 3S, 3P and 3D. There will be no 3F subcell. For fourth cell, N is equal to 4, that is the N shell, and when N is equal to 4, L will have value 0, 1, 2 and 3. L is equal to 0 means S subcell, L is equal to 1 means P subcell, L is equal to 2 means D subcell, and L is equal to 3 means F subcell. So the N cell, that is the fourth energy level, will have 4 subcell, S, P, D, F, and these are designated as 4S, 4P, 4D, 4Fs. So G subcell will not be present in the N subcell. G subcell will not be present in the fourth cell, because for G subcell L will be equal to 5, and when N is equal to 4, the maximum value of L will be equal to 4 minus 1, that is 3. Then the third one, that is the magnetic quantum number. The magnetic quantum number will determine, it will represent the orientation of the subcells in an external electric field. So the subcells can only take some discrete orientation due to space quantization, and the different orientations of the subcell are called atomic orbit. So the magnetic quantum number represents the atomic orbitals. The value of m depends upon the value of L, and for each value of L, m can have value 0, plus minus 1, plus minus 2, plus minus 3, dot dot, plus minus L. That means when L is equal to 0, that's for S sub cell, m is equal to 0, there will be only one orientation. For P sub cell, L is equal to 1, m will have value 0, plus 1, and minus 1. It means for P sub cell, there are 3 different orientations, and each orientation represents one atomic orbital. So P sub cell has got 3 atomic orbital, px, py, and pz. Then for D sub cell, L is equal to 2, and m will have value 0, plus minus 1, plus minus 2. So how many values, children? 0, plus 1, minus 1, plus 2, minus 2. So for D sub cell, L is equal to 2, and m may have value 0, plus 1, minus 1, plus 2, minus 2. That means 5 value. That means D sub cell will have 5 orientations, and each orientation represents one atomic orbital. So D sub cell has 5 d atomic orbital, and these 5 d atomic orbitals are dxy, dyz, dzx, dx square minus y square, and dz square atomic orbital. So here, this is then S atomic orbital. It is spherical in shape. P atomic orbital, it has got dumbbell shape. So this dot dot dot, they represent the probability of electron around the nucleus. And P sub cell has got 3 orientation, and each orientation represents one atomic orbital. Px, this atomic orbital is along the x-axis. Py, it is oriented along the y-axis, and Pz, it is oriented along the z-axis. So P sub cell, L is equal to 1, m will have 3 value, 0, plus 1, minus 1. That means P sub cell will have 3 atomic orbital, which are represented as px, py, and pz atomic orbital. And already I told you, D sub cell has got 5 orientation, because for D sub cell, L is equal to 2, and m is equal to 0, plus minus 1, plus minus 2. That means D sub cell will have 5 orientation, which are dxy, dyz, dzx, dx square minus y square, and dz square. And the shape of d orbital is different from p orbital, and d atomic orbital has got double dumbbell shape. So you can see it in your books. Then the 4th quantum number, has already told you that when the electron revolves around the nucleus, it also spins. The spin may be clockwise or it may be anti-clockwise, and the spin quantum number, it is represented by ms, and it can have value plus half or minus half to represent whether it is an up spin or whether it is a down spin, whether it is a clockwise spin or whether it is an anti-clockwise spin. So these are the 4 quantum numbers. The principal quantum number represented by n, it will represent the energy level. Azimuthal quantum number, it will represent the sub-energy levels. Magnetic quantum number, it will represent the orientations of the sub-energy levels in electric field. And the spin quantum number, it will represent the electron spin. It may have value plus half, or it may have minus half, representing clockwise or anti-clockwise spin. So friends, just we are coming into this atomic structure lecture series. Only 2 slides left. Then this is the Pauli's exclusion principle. What Pauli's exclusion principle states? 2 electrons in an atom cannot have all the 4 quantum numbers identical. 2 electrons can have 3 quantum number identical, that is the first three quantum number, n, l, and m. The fourth quantum number will be different. It is similar to a situation that two students in a school, same school, may have same name. They may belong to the same class. They may belong to the same section, but their roll number cannot be same. So two electrons, they can have same principal quantum number. They can have same azimuthal quantum number. They can have same magnetic quantum number, but their spin quantum number will be different. Like two students with same name, same class, same section, their roll number will be different. So from this, we will write electronic configuration. So electronic configuration is a shorthand notation by which we can describe the distribution of electrons in an atom. And the electronic configurations, the electron will first enter the lowest energy level, and when the lowest energy level is filled up, the electron will move to high energy level. And this is what is given by Bow principle. This is the Bow principle. The electron will first enter 1s orbital, and after electron entering 1s orbital, it will enter 2s orbital, and after 2s orbital, it will enter 2p, then 3s, then 3p, then 4s. After 4s, electron will go to 3d, then 4p, then 5s. So this is a diagram by which you can find out the order of filling the sub-energy levels by the electrons. So electron will fill the sub-energy level in order of increasing energy. So electron will prefer to occupy the next high energy level only when the lower energy level is completely filled. And each atomic orbital can accommodate maximum of 2 electrons, then with parallel slit. So S subcell, the maximum intake is 2 electrons. P subcell, maximum intake is 6 electrons. D subcell, maximum intake is 10 electrons. F subcell, maximum intake is 14 electrons. So 2 electrons, 6 electrons, 10 electrons, 14 electrons. So with this, I'm coming an end to this lecture series, and I was very happy to be with you. So if you have any query, so kindly drop me an email at vedanta69@gmail.com, or you can also send me WhatsApp in my number 985-999-2020. So at last, if you have any query, you can send me mail or send me WhatsApp. And if you enjoyed this video lecture, and if you think it is helping you to understand atomic structure, so kindly subscribe my channel so that you can get your timely update and share your channel with your friends. So with a promise that I will be back soon with some video lecture in some interesting topic. Until then, it is goodbye.